Welcome to the session. We are continuing with transformer. We have studied the real transformer, how a real transformer will be different from that of an ideal transformer. We saw that in case of a real transformer, uh, the fact is all of the flux generated by the voltage applied on the primary side does not link with the primary and the secondary windings of the transformer. Some of the flux is lost, and this drop in this lost flux, this air gap leakage flux, basically contributes to voltage drop. So from the primary end of the from the terminals of the primary end to the terminals of the secondary end, there will be drop in voltage twice rather, and this drop in voltage uh, needs to be uh, uh, needs to be seen how this can be modeled using the equivalent circuit of a transformer. So we are actually continuing with the analysis of a real transformer. So for deriving the equivalent circuit of a transformer, we need to study some things. Today, first of all, we'll be touching with the concept of magnetization current. So as far as the magnetization current of the transformer goes, it is actually the current that is applied at no load. So if we are not loading the transformer, the secondary side of the transformer is open. There will be still some amount of current that will be flowing through the primary windings, and this no load current that is actually flowing through the primary windings is referred to as the magnetization current. There are actually two currents that will be flowing at no load. One is the magnetization current IM, and secondly there will be uh, current that will be compensating the eddy current and the hysteresis losses in the system. So you can say the second current, eddy current and hysteresis loss. So this will be actually IE plus IH. So you can actually refer to this as the total core loss current in the system. So there are two currents that are flowing at no load. One is the magnetization current, and second one is the eddy current and the hysteresis loss. These two combined are actually known as the excitation current. So excitation current is the current that's actually flowing at no load in the primary of the transformer, in the primary winding of the transformer, and it is composed of two components, the magnetization current and the current that is responsible for core loss. Now, as far as this magnetization current goes, this is the current that is actually used for producing the flux in the transformer. Right? So this current, the magnetization current, is actually responsible for production of flux. We want to actually see the profile of both the IM as well as the core loss current, and therefore we want to see the total profile of this excitation current IE. So uh, once we know about these three currents, how they look as compared to the primary voltage that's applied to the transformer, we'll be able to model them using certain parameters like resistance, inductance, etc. Right? So as far as the magnetization current goes, it is responsible for generation of flux in the transformer. So we know how the magnetization curve uh, is. So this is the flux of the transformer, and as compared to the current flowing in the system, the flux, or you can say with respect to mmf of the transformer, the flux profile looks something like this. It's basically saturated. After some amount of time, the flux is saturated. It will no longer rise. There will be no longer, uh, there is a point where flux no longer increases beyond a certain point. This is your magnetization curve that we are familiar with, how flux rises in the system with respect to the current, fine. And this is the applied voltage in case of our system. So this is our applied voltage Vp to the primary side, and let us say this is Vm cos omega t. This is the applied voltage, and Vp equal to Vm cos omega t. This is our flux. Now we saw last time that the average flux in the system is given by integral of Vp dt divided by Np. So if Vp is equal to Vm cos omega t, integral of that will give us Vm sin omega t divided by Np. Right? So this is the profile of Vp equal to Vm cos omega t. This is the profile of flux as it saturates. This is the profile of flux with respect to time, with respect to omega t rather. So this is our average flux of the system. Uh, so this average flux is Vm sin omega t divided by Np. So you can actually see that average flux and the applied voltage Vp, they are actually having a phase difference of 90 degrees. Vp is equal to Vm cos omega t, while as your average flux is Vm by Np sin of omega t. So using these two, we can, having the knowledge about flux, average flux, and having the knowledge about the primary voltage that's applied to this system, we can superimpose them and find out the value of magnetization current. This will be somewhat like this. Fine. Superimposing our knowledge about phi with respect to I and our knowledge of phi with respect to time t, we can derive the profile of current with respect to omega t. So this is our omega t, this is our omega t. Fine. So this is our current now with respect to omega t. So you can see, because of the saturation effect here, the current that is generated from this, the current that's actually responsible for production of this flux is basically saturated at the top. That means there is a peak, and the saturation of flux causes the profile of current to be non-sinusoidal in nature. Why? The saturation of flux with respect to current, saturation of flux causes this current to be non-sinusoidal. Fine. So we have Vp equal to Vm cos omega t. So using Vp, we can find out average flux equal to Vm by Np sin omega t. Now we know that this is our Vm, this is our flux with respect to time, and this is our flux with respect to current. So we have flux with respect to time, we have flux with respect to current. So using those two graphs, we can find out current with respect to time. And if you plot this, you'll find out that current is, with respect to time, is basically somewhat of this shape. Fine. So you can, because of the nature of saturation, that there is a saturation effect beyond which basically flux does not remain, does not increase in the system because of the alignment of the domains, the magnetic domains of a certain material. The flux gets saturated, it will not increase further with respect to current. So you see the profile of current. This is actually which current? The magnetization current that's actually responsible for generation of the flux will be non-sinusoidal in nature. Fine. So this is an important concept that you need to note about the magnetization current, and that it is non-sinusoidal in nature. This is and also it is with respect to Vp, the magnetization current basically lags behind the Vp by 90 degrees. So you have actually Vp is the applied voltage to the transformer, to the primary of the transformer. It leads the magnetization current by 90 degrees. Right. So two things you need to note. One, this current is non-sinusoidal. Two, lags Vp by 90 degrees. Fine. Now this is the profile of the magnetization current of the transformer, non-sinusoidal and lagging behind Vp by 90 degrees. Fine. So you can actually have an idea that magnetization current, since it is lagging behind voltage by applied voltage by 90 degrees, so what parameter can you use, what physical parameter can you use to model the magnetization current? That will be an inductance, because you know that current from an inductance lags behind the voltage, applied voltage by 90 degrees. So we'll get to that. So for now we have seen the profile of Im. Im we have deduced from the knowledge about the saturated flux and from the knowledge of flux with respect to time. This is one component. Second component is basically the eddy current and the hysteresis loss, that's the total core loss in the system. The total core loss in the system is response for because of which some current will be uh, we are having some current that contributes to that power loss, that core loss in the system. Now the nature of this core loss uh, current. So if this is Vp, what we know about a core loss current is that core loss is basically proportional to d phi by dt. So if phi average is now Vm by np sine omega t, so differentiation of that means it will again be a cos function. So if this is Vp and this is phi, since the core loss current is proportional to d phi by dt, it will again be cos function, and therefore the core loss current will be in phase with Vp. Fine. Only thing here will be that it will not be sinusoidal, again sinusoidal in nature. It will be a non-linear current. Why will it be non-linear? Because of the effect of hysteresis. We know that this is the hysteresis loop that you are aware about. So there is a saturation point beyond which the current will not increase. So your current will not increase for in both the positive half as well as in the negative half. The current will be saturated because of the effect of hysteresis, and because of the need, because also because it is directly proportional to d phi by dt. The current will be uh, in phase with Vp, but it will be non-linear in nature. So regarding the core loss current, you need to know that this is regarding the magnetization current. A, it's non-sinusoidal. B, it lags behind Vp by 90 degrees. Regarding the core loss current, you need to note one, it is in phase. If it's in phase with Vp, the effect is that uh, we can use a resistance to model the core loss current, the core loss component. Fine, but it is also non-linear in nature. We can actually have a non-linear resistance in that can be used to uh, model the current law core loss current component. Fine. So you have the magnetization current derived that actually is responsible for generation of flux. that links the primary and the secondary winding, that actually is responsible for transfer of energy to the secondary winding. One, and secondly, you have the core loss current. Uh, that is actually because of the nature of the magnetic materials, you have certain losses in the system. One is the eddy current loss, and second one is the hysteresis loss. Together, they are known as the core loss. And we know about core loss that they are directly proportional to d phi by dt. Since phi is already sine omega t, so d phi by dt means it will again be a cos component. That means since Vp was also cos component, cosine wave, so so we can say that Ic is also being a cosine wave. Ic and Vp will be in phase with each other. So you have the core loss current, you have the magnetization current. So you can actually add these two up, Im plus Ic. You will get the current that is known as the excitation current. So the profile of excitation current will look something like this. Right? So this is your combined magnetization current plus core loss current in the system, that is together known as the excitation current. Excitation current is therefore the no load current that is flowing in the primary of the transformer, responsible for generation of flux as well as contributing towards the core loss components of the system. Uh, Two things important you need to note: magnetization current lags Vp by 90 degrees. Core loss current is in phase with Vp. Fine. So this is about these two current components. So uh, moving on, having the knowledge about the magnetization current and the core loss current of the system, we'll go for the derivation of the equivalent circuit of a transformer. Uh, so while designing the equivalent circuit of the transformer, we need to keep in mind the fact that equivalent circuit, as I've already discussed with you before, also it's actually a representation of the total electromechanical electromagnetic device that we have here. That's the transformer, using an electrical circuit and electrical network that will be useful for us for analyzing its transient as well as steady state behavior of the system, so that we can be able to calculate the efficiency of the system, efficiency of this transformer, the voltage regulation of this transformer, be able to find out the various losses in the system, and for that, representing and modeling each and every component of this electromagnetic electromechanical system using electrical equivalents. Fine. And the fact is, when we apply the voltage to a transformer, all of it is not converted into useful energy. Some of this energy is lost. So this energy loss in the system needs to be modeled so that our system is able to find be able to accurately reflect the true nature of the system. Our equivalent circuit should be able to reflect the true nature of the system that is being modeled. So what are the different losses in the system that we need to consider? We have the copper loss. We know copper loss is simply I square R losses in the system. So as far as I square R losses in the system go, so the winding, because it has some resistance, every winding that will be taking up will have some resistance, and because of the current flowing through that path through the winding, uh, loss power loss that is will be reflected there is known as the copper loss, which is actually in the form of heat. So this loss can be modeled simply using a resistance. So in short, the copper loss, uh, owing to the resistance of the winding, there will be power loss in the system known as the copper loss. That will be actually in the form of heat, calculated using I square R simply. So this loss is very easy to model, and we can model it using the resistance. Fine. Second one, you have the core loss in the system. Core loss, that is IH plus IE. Fine. So H plus IE, the hysteresis loss and the eddy current losses, as we saw just core loss, they are actually in phase with the voltage, the applied voltage of the transformer. And we know that the model, something that's actually, if you have a system that is wherein your current through that system is actually in phase with the applied voltage, and that system has to be resistance. So this will also be modeled using resistance. Thirdly, you have to take into account the magnetization current. As far as the magnetization current in the system goes, uh, we just saw the profile of IM, and we saw that IM is actually responsible for generation of flux in the system, but it is also in it is uh, lags the applied voltage by a 90 degrees. So if something lags behind the applied voltage by 90 degrees, it has to be modeled using an inductance. Fourthly, we need to take care about the leakage flux. We saw in the last session that the leakage flux contributes to two losses in the system, uh, both in the primary winding as well as in the secondary winding. So you have primary winding leakage loss and you have secondary winding leakage loss. That is actually responsible for ELP and ELS. Now, as far as the leakage flux goes, you have ELP and ELS. You have NP equal to d phi LP by dt and NP equal to d phi LS by dt. So how to model them? We know that phi is equal to, in this case, phi LP is equal to NP into I divided by the reluctance. Fine. Ni divided by reluctance. So similarly, on this side also, you have phi ls equal to ns, the number of turns of the secondary winding, into current divided by the reluctance of the system. So if we substitute this here, ELP will be equal to n square P divided by reluctance into di by dt. This will be actually dip, this will be dis, and ELS will be equal to n square s ns square divided by reluctance dis by dt. So you know this equation ELP equal to n square p by r dip by dt is nothing but L dip by dt. LP dip by dt, and ELS is L S dip by dt. Instead of writing LP, I'll write LLP and LLS. That means actually this is the leakage inductance. So L basically here represents the self inductance of the system. So both these two components, that is the leakage flux in the primary winding and the leakage flux in the secondary winding, they can be represented using the self inductances LLP and LLS. Right? So totally now modeling the system, what we have is this is your applied voltage 1. There is RP to model the copper loss components. So you have the primary winding. It also has resistance, contributing its own copper loss. You have the secondary winding. It will also be having resistance, contributing to secondary copper loss. Secondly, you have this self-inductance component, LLP. So this LLP is basically responsible for leakage flux in the system. Then you have RC. RC basically will represent this component, that is the core loss component. Fine. So since core loss current is in phase with VP, we have to model this in parallel to VP. Uh, and we'll have to model the magnetization current, you will have Lm, another inductance here, and this represents your primary winding. Now Rc and Lm, they are in phase, they are in parallel to Vp, because if we take them in series, because of the drop in Rp and LLP, then same voltage will not be applicable across Vp. Then we cannot actually say that Rc will, the current flowing through Rc, that is Ic, and the current flowing through Im will be IC will be in IC has to be in phase with VP, and we can show that only if we assume that VP is also being applied to the core of this system by placing it in shunt. Similarly, I am being in shunt to VP. We can say that the current IM will be lagging behind VP by 90 degrees. So this represents your primary winding. Your secondary winding similarly will have RS representing the copper loss component on the secondary side, and LLS representing the leakage flux on the secondary side. So this is your exact equivalent circuit. This is ES, the voltage available here. This is EP, the voltage available here. So you have to model each and every power loss component in this system to find out whether you to find out the equivalent circuit of the transformer. You have to model the copper loss in the primary winding using a resistance. You have to model the copper loss in the secondary winding using a resistance. So both these two windings will have some resistance to offer to the flow of current. We need to model that. Then you have to model the core loss component. Core loss, what we saw is that it is in phase with Vp, so we can model it using a resistance. Magnetization current is in lags behind Vp by 90 degrees. So place it in shunt, model it using an inductance. As far as the leakage flux goes, uh, they contribute to voltage drop in the system on both the primary side as well as on the secondary side. So you have to model them using two self-inductance components, LLP and LLS. Right? So uh, assuming that IP is the current flowing in the primary winding, IS is the current flowing in the secondary winding, you can see that VP is not equal to EP because there will be a voltage drop in the system, and Vs is not equal to Es if Is is greater than 0. If Is naturally some current is if the secondary side is loaded, Is will be non-zero, so Is Rs will be the voltage drop in the secondary side, so Vs is not equal to Es. So from primary voltage Vp to Vs, the voltage is not same. Uh, there's no there are power losses in the system, as well as the phase difference between Vp and Vs. It will not be a integral multiple of 90 degrees, right? Phi rather. So this is about modeling the equivalent circuit of the transformer. This is referred to as the exact equivalent circuit of the transformer. We do not use this exact equivalent circuit for analysis. We use uh, approximate equivalent circuit for analysis. To model the approximate equivalent circuit, we need to actually refer the secondary side of the transformer to the primary side of the transformer. Note that this winding here is actually only a representation now that this is a transformer. It has no other role here, and we need to specify the turns ratio of the system equivalent to A. So using the exact equivalent circuit, we'll be seeing now how to derive an approximate equivalent circuit. So wherein we will try to reduce components one by one and see how we can which components we can actually neglect, which components we cannot neglect. So that we'll do in the next session. So this is your exact equivalent circuit of the transformer, but we'll not be using this circuit for analysis of the transformer for deriving any voltage extra, for deriving the power loss or the performing any tests on the transformer. So for that we need the approximate equivalent circuit. We'll do that in the next.